Before we get started, I want to make sure that you guys have access to the OneNote classroom for this. So I updated this link so it works correctly. If you click it, I clicked it earlier so I wouldn't have to wait for it to load. It will take you to the web version of OneNote so you can look and this is today's lecture that I just clicked on. So you can see the slides I'm going to be doing today if you want to. Usually, but not today. Today I was ahead of thing. Usually I don't post them until after class, and then you can see my annotations. Now you'll just see it without the annotations, but you can see the slides. Here's the first quiz you had. And the second quiz, I haven't moved over here yet because, don't want to have that available to you before class. So let's go to the quiz we just did and look at the answers. It shouldn't be untitled page, but I should have, I thought it was going to be already loaded. All right. Well, it was supposed to be there and it's not. Oh, wait, this one. Maybe I'm just the one who's making mistakes. Impossible. Number one, what phase is the moon when we observe a solar eclipse? We talked about this last night in review. In fact, I think we talked about all these in review. What is it? Okay, a new moon, because for a solar eclipse, you have the sun, the moon, and the earth. Clearly, this is not drawn to scale, so that the shadow of the moon is falling on the earth. And so if you are on the earth, you're seeing the side of the moon that the sun does not see. Hence, the moon is not bright, it's dark. That's the new moon. Number two, what happens to the force of gravity between two objects if the separation between them is doubled? It is not halved. It's quartered.
I knew it.
Force of gravity is a constant times the product of the two masses divided by the separation of the centers squared. So you're going to divide by two. Well, let's just do it. Real quick math. I'm going to put in 2R for the top one and 1R for the bottom one. Now we can just cancel away like crazy people. The G's cancel, the M1s cancel. The M2s cancel, and the R squareds cancel, and I'm left with 1/4 over 1 over 1, or 1/4. Number three, what is the phase of the moon when it looks like a D? Remember that? And so this here was first quarter. This was full. That was third quarter. So third quarter it is. And finally the last one. And this is the one that I said, should I put this on or maybe I should put this on the quiz tomorrow. Yeah. I did. There was lots and lots of foreshadowing on this. Mostly in the very direct line of. Okay, so what is the importance of that equinoctial fluid? So important that it's one of the 5 things you have to point out specifically in lab.
It's like the equivalent of the prime meridian.
It's equivalent of the prime meridian in the sky. It's where we measure 0 right ascension from. Prime meridian on Earth is where we measure 0 latitude from. Over this or all over this? Because they kind of have opposite meanings. So the correct answers here were D, C, C, D. And course, my goal is that you knew them all. So I hope you did. Any questions about the quiz? We have a test coming up in what, a week and a half?
What day is it? Friday? Is it on a Friday? It's next Wednesday.
Oh, it's next Wednesday? Okay, in a week then, in a week.
Day after physics test.
Oh.
Get this time to study after.
Oh. Why? Where's the world so
Because we love you. And this time I can't say, hey, I don't know when the other teachers have their tests.
It's the same teacher.
It's the same.
I know, that's why I said this time I can't say it. Okay. I work my schedules independently and don't notice these things.
I could be wrong. That's what I had in my calendar.
Okay, so we're going to talk about light today. So, starters, I just took this picture. I didn't change anything else. This is James Clerk Maxwell. I always have to point this out. You'll never be tested on it. His family name was Clerk, but his father inherited some property and the title. Actually, I think it was just he inherited property, and he adopted the title Maxwell from the people he inherited the property from. And so the Maxwell is an added name. We call them Maxwell's laws, but it's like last name really wasn't Maxwell. Clerk Maxwell. Okay, so he came up with 4 laws that govern all of electricity and magnetism. It's pretty amazing. When he started out, there were lots and lots of different equations people had put together. And he winnowed through, and first he lowered it to somewhere in the teens, or maybe it was 22. And then he finally came up with just these 4 equations to describe all of electricity and magnetism. If that was all he did, I wouldn't be mentioning him for astronomy. Physics, of course. But then when he looked at those 4 equations, he realized that if you combine those 4 equations, they predicted that electromagnetic waves could exist. That is, you can have a wave, like a water wave, except for instead of going through water, it's going through space with electric and magnetic fields. And so everything we do in astronomy is based on observations of something out there, and then applying the physics we know on Earth to out there. And so the electromagnetic waves are the way we do all of our observation. Hence, super important. You can't believe anything in astronomy if you don't believe in electromagnetic waves. So some terminology, some things to know about waves. One thing that's not listed here is the wave speed, the speed at which the wave travels. Electromagnetic waves, of which light is one example, travel in vacuum at 299,792,458 meters per second. That's called the speed of light in vacuum. Often we'll just say the speed of light, but the thing is that speed of light in vacuum is a constant. As soon as you put the light in something that's not a vacuum, like air or glass, it slows down. But that's the maximum speed. And you might see nerdy physicists wearing shirts that say 299, blah, blah, blah. It's not just a suggestion, it's the law. Because that's the ultimate speed limit for the universe. Nothing can travel faster than that speed. So that's the speed at which light travels through a vacuum. What is it between us and almost every other object? Pretty much just vacuum. Now I say just vacuum. We'll learn later, oh no, there are molecules in there. But we'll also know that what we consider a thick, dense cloud in outer space would be considered a vacuum on Earth. The lowest vacuums we can get on Earth have more molecules per volume than the dense clouds in space. So in space, that's pretty much the speed that the light travels. But it is important to put out there so you realize that we don't see things as they are. It takes time for the light to get here, so we're looking back in time whenever we look at something. Looking back minutes when we look at the sun. Looking back years when we look at the very closest star. The very closest stars, we've seen it more than 4 years ago. I know I mentioned this earlier, but now is when we're getting to the physics of it. Now, when we talk about these electromagnetic waves, we have either electric field or magnetic field that is oscillating. So the electric field is going strong, 0, strong the other direction, 0, strong. So it's oscillating back and forth. And so we talk about troughs, places where you have the minimum, a negative, electric field, the electric field pointing the most it will down. Places where you have crests, where it's the most it will up. And the wavelength is the distance to repeat. So in this picture, it shows it from crest to crest. They could have just as easily put it from trough to trough. Or they could have chosen any other place at all. They could have chosen, for instance, let's go when it crosses 0 here. Where does it repeat that? Okay, it repeats here. Why did it not repeat there? Yeah, it was still 0, but it was going the opposite direction. The change was the opposite direction, so it's not actually repeating. So you could have also said this is the wavelength. What's that? Lambda. That is a lowercase l in the Greek alphabet. L for length. Get it? So that lambda is the wavelength symbol that we use. So that's an important thing to know. Another thing that's important to know that's not on here, is the frequency. Let me change the color. Okay, so you can see I'm getting better at this, except for one thing. I have no idea why sometimes the controls are at the bottom and sometimes they're at the side. Still things to learn. Frequency, first let us define it. There's a certain frequency with which I go to church. How often do I go to church? Okay, assuming that I am a good churchgoer, since you may or may not see me there. How often? Once per week. The frequency is how many times per stretch of time. So how many occurrences per stretch of time avoids using the same word with two different meanings in the definition. So once per week is a frequency. Or your birthday comes once per year. Unless, of course, you're born on leap day, then your birthday comes once per 4 years. So frequency for electromagnetic waves, we're usually talking very high frequencies. Things on the order of 10 to the 14th hertz. What does hertz mean? Hertz is a shortened form of saying 1 per second. So 10 to the 14th hertz means 10 to the 14th repeatings per second. That's a lot. What's 10 to the 14th? That's a 1 followed by 14 zeros. So we usually don't talk about the frequency in hertz when we talk about electromagnetic waves because they're really big numbers. The frequency relates to the wavelength with this equation. And if you don't know these symbols, which I assume you don't, you look at it and you say, that means nothing to me. Nothing. Well, F, you can probably figure out that's short for frequency. I could have used nu. Physicists often use the Greek letter nu for frequency, and then you would know less. What is the second symbol in that equation? The second one is lambda, which is the wavelength. So frequency times wavelength equals, and then what Alwan said, the speed of light. And if you're in vacuum, this is correct. If you're in air, then you replace C with V and be the speed, whatever medium. So this equation here allows you to relate the frequency with the wavelength. And for visible light, we almost exclusively describe it with wavelengths, the wavelength it has in vacuum. So red light has a wavelength of somewhere between around 700, 750 That's the longest wavelength we can see. Longer than that, we call infrared, below red. Now, you guys probably picked up that I was a nerd all my life. So, you know, when I was a kid, we're reading the World Book Encyclopedias, and I read about INFRARED, light. I read it as infrared. It seemed like good reading of English. But it's actually infrared, below red. So it's a frequency below red. If you go to shorter wavelengths, you get to the blue side of the spectrum. That's the shortest wavelength we can see. I say blue, some people say violet. Technically, violet is beyond blue. Anything that's a shorter wavelength or higher frequency than violet, we call ultraviolet, above violet. So the spectrum, visible spectrum, has infrared below, ultraviolet above, and we usually talk about the wavelengths when we're describing it. So the wavelength can be calculated simply by taking the speed of the wave divided by the frequency. So here is a picture showing the spectrum. Now I am going to zoom in. I say I'm going to zoom in. Let me say maybe. Depends on how things work. That's not it. When I tried this before, it's none of those. When I tried this before, there's the icon for zooming in. When I tried it before, it did not work the way it's supposed to. Okay, so now I can zoom in. Here we have the spectrum of electromagnetic waves. And I cannot write on it when it's zoomed in, so I'm not going to try to. But if you notice on the left-hand side, you have the wavelengths on top, and you have 0.0001 nanometers here. NM. N, prefix for nano, means 10 to the minus 9. It's a really tiny number. We use the prefix nano, and that is what we commonly talk about. We'll talk about wavelengths in nanometers. So gamma rays have very, very short wavelengths. How long is 10 to the minus 9 meters? This is a meter. Divide it by 10, and you get a centimeter. Little marking right there. Divide that by 10, you get, okay, that was 100, excuse me. Divide it by 100. If you divide it by 10, you get something called a decimeter. Nobody ever talks about decimeters. You divide it by 10 again, and then you get the centimeter. Centi means 100. That's why there's 100 cents in a dollar. Divide it by 10 again, you get milli. If you take a millimeter and you divide it by 1,000, you get a micrometer. So 1,000th of that little thing is a micrometer. 1,000th of a micrometer is a nanometer. Very tiny. Gamma rays are 1/10,000th of that for their shortest range. Extremely short wavelength. You get up, you have, notice X-rays here. Interesting, now it's not showing the hand like it did before. There we go, now it's X-rays. X-rays and gamma rays are only distinguishable by the source. Gamma rays are coming from the nucleus of an atom. X-rays are coming from electrons that are bound to the atom. So it's the source that actually makes the difference. As far as you're concerned, those are just very short rays. Ultraviolet rays, technically all of those ultraviolets, the sources that make the difference from X-rays, gamma rays, versus ultraviolet being all of them. Why does it have CAT scan shown here with X-rays? I don't know, because a CAT scan is using X-rays. I'm not sure why you need to specify CAT scan in there, because it's just using X-rays. Okay, visible spectrum. You see the visible spectrum is a fairly small portion of this entire electromagnetic radiation spectrum. Then we get into infrared, and notice it shows TV remote. Yes, your TV remote uses infrared radiation. Excuse me?
That's why the same reason the CAT scan kind of give them so we can.
Yeah, something common, but X-rays, don't you still get X-rays all the time? Anyone here have an Android phone?
I do.
Does your phone have a little thing up here in the top?
What?
No, yes?
Like a little dot?
It should look kind of like a window, a little glass window.
Okay, it has it. I think I know what you're talking about.
at least some Android phones, they came with a little LED, infrared LED transmitter, so you could use them as remote controls for your television.
Really? Oh, I don't think this
Wow.
Well, actually, that's not the purpose. The purpose is for them to communicate, so you could be in the classroom. Okay, you should never, ever do this. I know you can cheat with things like there are some, this does not, but there are some calculators that also do this. But it's for communication. Probably don't have them much anymore because these days you use other things. Anyway, our tablets that we use for, you might have some class where teachers teach with a Samsung tablet. Those have one as well, so you can use those to control your television, which is cool. Then we get to microwaves. What do we use microwaves for all the time? Okay, food is what you're saying, but what you use it much more for is using your cell phone. Your cell phone is communicating via microwaves. Electromagnetic radiation. Then we have, radar there just to make you angry. Unless you're looking out for weather. And radio waves and TV waves. All of those are electromagnetic waves. They're all the same phenomenon. What is different is the wavelength or the frequency that's used. Now notice in the visible spectrum, we have it broken out here, and you can see red goes from about 750 nanometers to violet over here, a little bit below 400 nanometers. The reason I always use 400 to 750 is because if you calculate the frequency that goes with the wavelength, 750 nanometers is 4 times 10 to the 14th hertz for the frequency. And 400 nanometers is 7.5 times 10 to the 14th hertz for the frequency. So then I only have to remember 4 to 7.5, 400 to 750 is the same numbers. That's the actual reason why I always choose 750 and 400. So here's back looking at the whole thing. In astronomy, these different portions of the spectrum are important to us because we can see different kinds of details with different wavelengths. So the top of this picture shows the kinds of things you see. Gamma ray bursters and gamma rays. X-rays, you see pulsars very strongly. Visible light, well, that's everything we see when we go out to look at the sky. And then if you get to microwaves, you can see, radiation coming from gas, like hydrogen gas. You can see the remnants of the Big Bang, what we call the cosmic microwave background radiation. That is in some pretty long wavelengths. And so there's different types of things we see in astronomy with different wavelength ranges. So there are telescopes made to work in all of these different ranges to gather as much information, different kinds of information from different kinds of telescopes. Okay, so looking at these have been coming forward as I press the button. Radio waves are very long. They're not sound. I, as a kid, kind of thought that maybe radio waves were sound waves, and the radio was amplifying. No, the sound waves are encoded on the electromagnetic waves. And the sound waves, they're waves, so they have wavelengths and frequencies as well. But sound waves, what we hear, range in frequency from about 20 hertz for the very lowest pitch you can hear to about 20,000 hertz for the highest pitch you can hear. Those are much lower frequencies than frequencies for light waves. Microwaves, yes, we cook with them. We use them for communications. Infrared, well, you can cook with infrared too. Infrared's actually very efficient for heating stuff. Your body is giving off a lot of infrared radiation. How many people knew that? Okay, yeah, at least one. When you look at say the U.S. is bombing Iraq. I use that for example because when I started teaching that was going on. You turn to CNN and they show you these night vision views and you see the town and all of a sudden, big splash of light. The night vision is looking at the infrared radiation because you're giving off infrared radiation. You can be clearly seen in infrared light. And so it is useful if you were a hunter out there, infrared would be good because you'd be able to see the animals in the dark. Now we have the stuff that's above visible. Ultraviolet is really all of it. X-rays come from electrons bound to atoms jumping down. And X-rays obviously go through a lot of material, hence we take them for our bodies. And then gamma rays, the shortest, coming from the nucleus. On Earth, the only kinds of rays that make it to Earth are visible light and radio waves. Why doesn't the rest of the electromagnetic spectrum reach the Earth? Okay, the atmosphere. The atmosphere is blocking it. Now, there's really importance and significance for us in this graph. You guys, I'm sure, have all heard of global warming and the greenhouse effect. The greenhouse effect has everything to do with this graph. The greenhouse effect is we have radiation from the sun that comes to the Earth. The sun's peak radiation is in the visible spectrum. And you notice that visible light comes through the atmosphere. So the peak energy from the sun gets through. Yes, there are some parts of the sun's radiation that are ultraviolet that gets blocked, some that's infrared that gets blocked. But the bulk of the energy coming from the sun comes right through. It heats the Earth, but the Earth is not nearly as hot as the sun. And so the Earth is giving off radiation, but its radiation is much longer wavelength. The Earth's radiation is in the infrared range. And so the Earth's radiation is largely absorbed by the atmosphere. Hence, energy comes in but can't get out. In that case, the temperature of the Earth is going to rise because the energy is increasing until you get the Earth hot enough for a balance. Well, the whole idea of man being responsible for global warming is that man is contributing gases that make it absorb better out here where it's allowing some through and not, where it's just starting to allow it through. And if we are emitting gases that are making it so the atmosphere is more absorbing, not letting the radiation out, then it's going to cause the total energy to go up some more, making temperatures hotter. In astronomy, we do concern ourselves with such things, but more, especially for right now, observation, we can make telescopes that view visible light. We can make telescopes that view radio waves on Earth. That's going to work well. But if you want a telescope that's going to look at X-rays, it's not going to work very well on Earth because the X-rays don't get through the atmosphere. So what are you going to have to do if you want to make an X-ray telescope? You're going to have to launch in space. You're going to have satellites to make the observations. Now, it does show a satellite here. What satellite is that? Yeah, that's the Hubble Space Telescope. Now, the Hubble Space Telescope, if all goes as planned, will eventually be replaced. Anybody know what the replacement for the Hubble Space Telescope is? Oh, that makes me a sad panda. Okay, so you can't read the last letters. The replacement for the Hubble Space Telescope is the Webb Space Telescope, which I think it was originally supposed to be launched this year, then it was pushed off, and I think it's now been pushed off, not being launched next year either. The Webb Space Telescope, sadly, is the James Webb Space Telescope, and I'm not related to James Webb, but he was the first administrator of NASA or something, first head of NASA. So I just want everyone to know it's the Webb Space Telescope. That's the one that's going to replace the Hubble. It will be a better telescope, giving us much better resolution images. You guys don't know that. Here's a map of the sky using X-rays. Oh, actually, I want to go back to this. I want to talk a little bit about evolution. I'm not going to ask you how many people believe that life evolved because that's kind of a sensitive question around here. But let's talk about evolutionary pressures. Do you guys understand the theory of evolution and how evolution is driven according to science? Vaguely, yeses. Well, the basic idea of evolution is that you have survival of the fittest. That is, the things that have advantages are more likely to live than the things that have disadvantages. You know, we can take gross examples. If you have an animal that's born and its mouth won't open, it's probably going to starve, right? And so it won't survive. So if you have two variations of the same animal, and one of those mouth just opens a tiny mouth and it has to try to eat all day long to survive, another one's mouth opens bigger and it can eat quickly and only has to eat for half the day to survive. Well, the one only has to eat for half the day has some big advantages. It has time to reproduce. So the theory of evolution says if you have some variations that occur in a species, if one variation makes it more survivable, then that one's numbers are going to go up, and the other one that's less survivable is just naturally going to decrease until you have a transition. And so evolutionary theory says everything that we've developed is developed under that guiding principle. Something that's going to help us is going to stick around. So now I want to use this and this graph to talk about our vision. We see in the visible colors, which is one of only two ranges that, okay, we call it the visible color because we see, I know that was redundant. Only one of the two ranges that allows us to see through the atmosphere and see the sky. If we had vision that was not in the visible range or in the radio range, it would have been much, much, much later before people even realized that there were other things out there, because we wouldn't see them. So now, evolutionarily, some might say that, well, yes, we developed the vision in that range because that's the light that comes through the atmosphere. But to me, that doesn't make sense. Because if our vision was based on evolutionary pressures, we would be much more survivable if we saw it infrared. Because what I've seen, if you're hunting, or if you're prey, if you can see animals in the dark, that is, you're not relying on the sun and the visible spectrum, you're seeing the radiation that's coming from the animals, it's going to be much more survivable. And so it would seem to me that if evolution was responsible for the development of our eyes, we would probably have infrared vision rather than visible light vision. Or maybe some combination of it.
We don't some snakes see infrared?
There are some animals that do, but they're not humans. And so I tend to believe that God created us. So you see where I stand here. I believe in divine creation. God created us with our color vision so we could see the skies and appreciate it. Yeah.
So then, you know how they say that like cats can see better in like the night than we can by far? Why is that? Does it have to do with this kind of like?
Well, if you look at the human eye, we have 3 different cones, and those cones are sensitive to different colors. And so we see in 3-color vision. How many people knew we saw 3-color vision? Probably everyone, if you actually analyzed, only one had already, raised their hand to indicate she'd already thought about it. But when you have a computer monitor, they usually say it's RGB. Why RGB? Because those are the 3 primary colors of light: red, green, and blue. Why are red, green, and blue the 3 primary colors of light? Because we have 3 kinds of cones. One cone that is most sensitive to red, one that's most sensitive to blue. Actually, yeah. And then the third one is between the 2. We call it the green one. It's actually more, its peak is in the orangish range, but it's the one that gives us the ability to see green. And so RGB, those are 3 primary colors for light. Or if you have a color printer, your inks are CYMK. C for cyan, Y for yellow, M for magenta, and K, actually it's not for black, it's for, I can't remember what it stands for. It's the black ink at any rate. And why CYMK? Cyan is white light, they're reflective, the inks, the pigments. And so cyan is going to absorb only one color, and that would be green. Yellow is going to absorb only one color, blue. and magenta. Oops, no, I said it wrong. Cyan is absorbing green. Magenta is absorbing. Oh, I keep saying it wrong. Okay. Cyan is easy. That's absorbing blue. Magenta is reflecting blue and red, so it's absorbing green. So cyan is absorbing red. And so your secondary colors or primary pigments are cyan, yellow, magenta. And if you take an art class and you learn different colors, it's because those are approximations to make it easy to find pigments. So they're approximations for cyan, yellow, magenta. Okay, now I'm going to move on. This is looking at the sky in X-rays. Looks a lot different than looking at the sky in visible light. Just going to move on from there and talk about temperature real quick. Temperature, hot or cold, right? But temperature actually means something. Temperature is measured proportional to the average kinetic energy of an object. Juliet last night read all the physics things we talked about. Kinetic energy, one of the types of energy in motion. Well, if I have a gas around me, like air in this room, each molecule is moving. It has kinetic energy. And the temperature is a number that's telling me about how much kinetic energy the molecules have on average. So higher temperature, the molecules have higher kinetic energy, which means they're going to hit me harder. When they hit me harder, they're going to transfer more energy to me, and I'm going to feel that as the heat sensation, the energy going in. And this shows temperatures for comparison. There is a minimum temperature when the kinetic energy is approaching zero. I say approaching because I sometimes am technical. The temperature the molecules cannot reach zero speed, zero kinetic energy, because of quantum mechanics. So absolute zero is the lowest possible kinetic energy state. It's not zero kinetic energy state. Were you going to say something on that?
No, I was going to say absolute.
So, yeah, absolute zero is the lowest possible kinetic energy, but not zero kinetic energy. And then you see liquid nitrogen. We know liquid nitrogen is really stinking cold, but you can see that it's 77 kelvins above zero. Kelvins is the scientific version of temperature. We, in the United States, use the Fahrenheit system. Fahrenheit, developed by Georg Fahrenheit, a German? Well, yeah, he is. A German. Was. He used, as far as we know, a centigrade system, 100 degrees between the temperature of icy ocean water and body temperature of a cow as his two reference points for 0 and 100. Just a few years, like within 20 years, Anders Celsius came up with his variation, and Anders Celsius did things not the way the Celsius scale is. Anders Celsius took the temperature of boiling water to be 0, and the temperature of freezing water to be 100, which is upside down. There's an absolute zero, a minimum kinetic energy. There's no maximum. So within a year of Celsius dying, people flipped his scale over for him to make it so it made some sense there. That you're going to lower speed when you go to lower temperature instead of higher speed when you go to lower temperature. And then the Kelvin scale is based on the Celsius scale, just shifted by 273.15. So 273.15, 0 Celsius is 273.15 kelvins, or 0 kelvins, absolute zero, is minus 273.15 Celsius. Those are the common temperature scales. And things that happen to liquid nitrogen boils at 77 kelvins or minus 321 Fahrenheit. It's pretty cold. Water freezes at 273 kelvins, 0 Celsius, or 32. And you can go off water boiling. A light bulb filament. Light bulb filament is around 2,000 kelvins. Light bulb filament, that's this baby. The sun's surface, about 5,800 kelvins. And then you go to the core of the sun, about 15 million kelvins. It's really hot in the sun. Black bodies. Now I'm going to do something fun here. Well, I'd better do it now. To look at black bodies. Black bodies is the name for a perfect emitter of light, something that gives off light because it's hot and it does it perfectly. If it's not black, then it's not perfect. So I'm going to give you these glasses, which of course I want back. These are actually designed to be children's party glasses. And when we put them on, you will see great and mysterious things.
Is it like what we did in physical science?
What was that?
Is it what we did in physical science?
Uh-huh.
Oh, awesome.
Well, it's physics, so of course it's awesome.
Hey.
Oh my god.
Oh, shoot, you good, bro? Go to yourself. Somebody screwed up my blinds. Well, I'll close, but not so big one. Fix the other one later. It happens if somebody raises it too high. Okay, so I'm going to turn off the lights, and you can observe some cool things. But before I turn off the lights, notice the lights above you in class. If you look across the room at one of the lights, not just straight up across the room, what do you see?
Colors.
Colors. You should see not just colors, but sheets of color. Because these lights are just giving off specific colors. And what we see as a white light is actually the combination of those different colors you see for the sheets, which is really cool. Once again, we only see really 3 colors because we only have 3 cones. I started on that. The animals that can see in infrared have a different type of cone. Okay, so turn off all the lights except for these. I forgot to turn these off last night. I am going to take this filament and make it hot. So right now it's cool, and of course it's giving off no light. So now it's a little bit warm. And by a little bit warm, I mean it would burn me. But compared to a normal light bulb, it's nowhere close to that 2,000 kelvins. And so what color do you see it as? Orange, okay? And if you look off to the side, you should see kind of a rainbow effect. You see that?
Yeah.
So these glasses are doing what we call spectroscopy. They're breaking the light up into the different wavelengths. And so you're seeing closest to the light, you're seeing the shortest wavelengths. Farthest from the light, you're seeing the longest wavelengths. So you see red as the farthest color away from the light. And right now, what color you see closest to the light? Green. Now I'm going to heat it up. If I heat it up, what happened to the brightness? Did it stay the same, or did it get brighter or dimmer? Okay, it got brighter. So when you make it hotter, it gets brighter. And then if you look at the colors out here, they're of course brighter, and you can see now there's a little blue there.
Yep.
And what happened to the color when you added in some blue? It moved closer to white. It's a little more yellowish. So if I make it hotter some more, now you'd say, yeah, that's in the yellow range. So hotter got it more yellow. And you see now there's a very clear blue on the inside moving into violet. So the range of colors that's being produced is going to shorter wavelengths. We still have plenty of the long wave. We still have plenty of the red. But we're now adding in a lot of blue that wasn't there before. So I keep going hotter. It gets much, much brighter. And now the colors you see very strong all the way through the visible spectrum. So you can see some variation in the spectrum based on temperature. This is black body radiation, what I have in the picture up there. Now I'm going to turn this off and go to something else. This is helium gas. I put some energy through the helium gas and it gives off light. What color is the light, the center?
Yeah.
I would call it peach, okay? Because I love peaches. Maybe nectarine. That's the color. Good nectarine. But then if you look outside of that, you don't see a rainbow effect. You see specific lines. It's because this is giving off only those specific colors instead of a continuous range. This is a fundamentally different way of producing light. Instead of producing light because something's hot, it's producing a different way. We'll talk about the way it's producing in a later class period. Don't have time to continue on with this today. So we're going to stop with this. We'll probably bring out the glasses again in another class period. Let me show you a few more slides to finish up these ideas and maybe hopefully cement them in your heads.
So that, see that.
So the sun, by the way, note this picture, we have lots of sunspots. Those are storms on the sun, magnetic storms, that we'll learn about when we study the sun. So the effect we saw has to do with the molecules hitting each other. When the molecules hit each other, they give off some light. And so when it's hotter, the molecules are moving faster, they're going to have more collisions per second, hence more giving off lights per second, and it's brighter. And when they're hotter, they have more kinetic energy, which means more energy to convert into light, and it makes the frequencies go to, or the light go to higher frequencies or shorter wavelengths. So here you can see at low temperature, it's not very bright, and the peak is at long wavelengths. You make it hotter, the peak comes into the visible range, goes into the ultraviolet range, and it gets really hot. Two laws that relate these. Wien's law. I'm going to hide this 2 seconds before I hit stop. Well, less than a minute. Wien's law says the hotter the body is, the shorter the wavelength of the peak radiation. The Stefan Boltzmann law says the luminosity, how much light the object gives off, is dependent on the temperature. And we have numbers for those. Here's Wien's law. 2.96 million kelvins times nanometers divided by the maximum wavelength is the temperature of the object. Or you can replace or switch temperature in the wavelength max. The peak wavelength is 2.976 million kelvins times nanometers divided by temperature in kelvins. And likewise, we have the Stefan Boltzmann law. The luminosity is a constant times temperature raised to the fourth power. So if I double the temperature of that filament, it's going to be 2 to the fourth, or 16 times more light given off. Okay, time for us to go. Have a great hump day. Please do give me back the glasses.